Okay, so welcome to this session of NCTS Algebraic Geometry Seminar. Today we're very happy to have Sunny Sood from the University of Warwick, and the topic of his talk today is on the Hermitian K-theory of Grassmannians. So yeah, please start.
Thank you, and thanks, Flora, for the invitation. So today I want to talk about joint work with Junkai Zhu about the Hermitian K-theory of Grassmannians. In this talk, so I will describe our computation on of the Hermitian K-theory. Hermitian K-theory of Grassmannians. Okay, and just to give you some context, in the subject of K-theory, if you can compute something, you've done very well for yourself. So a lot of research is devoted in order to help you try to compute things. So computing something is a big deal. So yeah, that's what I'll talk about today. And let me just tell you the structure of the talk. So the talk is structured as follows. Okay. So I'll start off by very briefly. So very briefly. Good. So I will very briefly describe what K-theory and Hermitian K-theory. I will very briefly describe what this is. As my audience is algebraic geometers, I'm not going to assume you know anything about this. I won't go into a lot of detail, but I want to give you at least the intuition because this is ultimately what the subject is like I'm talking about. So motivation. Examples. Okay. And then after I've given you some intuition, so we'll describe. So I will describe the computation. So yeah, describing the computation also was non-trivial, so I have to explain some stuff. So going over every necessary detail to understand. Okay, so I'll go over everything necessary to understand at least its statement. Then I will outline the proof. Okay, and then finally I'll discuss some further problems. So discuss further open problems. Okay. Okay, so that's the plan for today. All right. Okay. So let me begin. So intuition for K-theory and mission. Okay. So right. Okay. So let me give some intuition. Okay. So we start off with so consider finally generated projective modules. Okay. So projective modules. Okay. over a ring R. Okay, that's fine. So that's at least when you first see K theory, that's what you consider. So note, we can um, add finally generated projector modules. Projector modules by a direct sum. Okay. Okay, so we can do this via direct sum. So then this gives us that if I denote, if I denote the collection of all finally generated projector modules over R as proj R, as this set. Okay. So if I denote this set by proj R, then proj R, and if I take isomorphism classes of these finally generated projector modules, and if I consider the isomorphism classes under direct sum, this is an abelian monoid. Abelian monoid. Okay. Okay. So because we have an abelian monoid, what we do is so we can take group completion. Group completion. So this is also known as taking the Grothendieck group and define so you can define K0 of this ring to be the group completion of this abelian monoid. So I denote group completion by superscript GP. Okay. And then you can compute in instances. So e.g. For a field f k0 of r, k0 of f is isomorphic to the integers because so intuitively proj r is just any finite generated projected module over a field is finite free. So taking direct sum is just adding the dimension of the vector space, and when you take group completion, you're formally introducing inverses, so you get the integers. Okay. This is cool. Any questions on this? Before, so that was a very quick overview. Okay, cool. Okay, that's fine. So the point is that you can, at least for the purpose of this talk, you can play the game. You can play the same game for schemes with schemes. And this is what Grothendieck originally did, right? So how do you do that? So if you let X be a scheme, so X be a scheme, and then if I denote by VB of X, so set of finite vector bundles, so vector bundles on X. So for me, a finite vector bundle is a locally free sheaf of finite rank, but and then we can define. Okay. Then we define K0 of X. Analogously, we define this to be VB of X. We take isomorphism classes, and we take the group completion of the abelian monoid. This guy. Okay, so you can do the same thing on schemes. Okay, so that's what K theory looks like, at least at the level of K0. But that's where the intuition comes from, and that's where things were started up from. And then what is Hermitian K theory? So, so let me give you a slogan. So Hermitian K theory should be thought of as the K-theory of quadratic forms. Quadratic. Okay. 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 And then I'll explain, but I just want to remark that because we introduced quadratic forms, there are deep applications of Hermitian K-theory to motivic homotopy theory. I don't know much about motivic homotopy theory, but it's very relevant in that space. So if you want to explore further avenues, then that is a good way to go. Anyway, yeah. So this is where it should be thought of, and then I'm going to make the following assumption straight away. So I will assume throughout that 2 is invertible in my base ring, so that the theory of quadratic forms is equivalent to the theory of symmetric bilinear forms. So to give a proper treatment of the subject without this assumption of 2 being invertible, you really, in my opinion, do need to pass to stable infinity categories. And recently, a few years ago, there was a series of 3 papers written by 9 authors that rewrote the foundations of Hermitian K-theory in terms of stable infinity categories. This was really monumental work. So one of the papers got published in the Annals, the other one got published in Acta Mathematica, so it was a very, very big deal. And because of this, it's a very exciting time in the subject because the framework is quite powerful and it leads to many new things. But anyway, so that's irrelevant in general, but even more so when 2 is not invertible. But throughout, I will assume that 2 is invertible just to make life easier, mainly for me, but also for anybody else. But yeah, so this is quite an important assumption. Okay, right. And then let me tell you intuitively what I'm dealing with. So intuition. Okay, so if I let P prime be in proj R, okay, and if I let, okay, so because this is the same as this with my assumption, I can let I'm going to consider symmetric bilinear forms. So P cross P into R, P prime. Okay, so B. Okay, throughout my bilinear forms will be non-degenerate. Okay, so I'll just say this one, but that's what it is throughout. So throughout, it's a non-degenerate symmetric. Okay. Okay. So then I can also do the same addition thing. So we can add. Okay. So how do we do this? So B. Sorry. B prime. B prime. So it's the first thing you can think of. This. It's traditionally done like this kind of. So let me where B prime, so X, Y is defined to be, you just do it component wise, right? So B of X plus B prime Y. Okay. So the point is you can add similar to as the above. So if I let if I call bil R denote the set consisting of guys of the above consisting of, so finite generally projected module with non-degenerate symmetric bilinear form. Then again, so if I consider isomorphism classes of such, this is also an abelian monoid, and I can take the group completion, and this is what I call GW0. Okay. Okay, so this is the zeroth Hermitian K-theory group over a ring R, and this is computable. So, e.g., let me compute. So GW0R. So of the real numbers, this is known to be isomorphic to Z direct sum Z. And then GW of the complex numbers, you can prove is isomorphic to the integers. So one can compute with these things, which is good. Okay, and then as above, so again, we can play the same game with schemes. So can play the same game with schemes. Okay, so if I let X be a scheme, and then, okay, so then crucially now I'm going to let L be a line bundle on X. Okay, so then I can take, if I define bil XL, so let this denote the set of L valued symmetric bilinear forms. So if I call this guy, so we're now so this V is a vector bundle, a finite vector bundle on X. Okay, and then I could define GW of X, this time with values in L, define this to be bil of X L, isomorphism classes, and take the group completion of this. Okay, I could have also taken different values of my bilinear form in this case as well. I could have replaced R by any R module of dimension 1. But yeah, so but in the point is, in the case of schemes, this becomes very concrete. So I could take L valued symmetric bilinear forms, and I can consider this guy. Okay, so any questions so far? So this is, I'm going to consider compute this, but generalization to higher GW groups. And I'll show you next how it relates to K-theory, but if there's any questions now, please ask. Okay. And let me tell you how they relate to each other. So note, so we have the hyperbolic, so it's called the hyperbolic map. Hyperbolic. Okay, so they're related by the following, right? So, okay, so in the context of rings, but again, this also works sort of for schemes, but let me just state it for rings. So there's something called the hyperbolic map, so which goes from K0 to GW of R, where I send V to V direct sum the dual of V. And I would define B where B goes like this. To R B of BF G is defined to be, so I just take it across my components. So f of w plus g of b. Okay. And there's also another map going the other way, so which is the forgetful map. So it's m. Where I simply forget my bilinear form. So this is how these two relate to each other. Okay. Okay. And then the co-kernel of H, the hyperbolic map. Hyperbolic map. So this is known as the Witt group. The Witt group. Okay. So if I take the co-kernel of this map, I get something called the Witt group on R. I could define this more intrinsically as well, but the point I'm trying to make is that this so that the point is the point I'm trying to make is that we have a short inexact sequence, so that we have exact sequence. Okay. And I forgot one thing, so let me just write this down. So this would be exact, but then, well, it is exact, but also one also writes, you take C2 orbits of K0R, where C2, so this is induced by the duality as an R module. Because here V gets mapped to this guy, then V dual will get mapped to V dual direct sum V double dual, but then because it's a finite generated module, finite generated projected module, V double dual will be isomorphic to V, right? So yeah, we can take orbits. Okay. So this is good. Yeah, and then any questions so far? Before I'm almost done with my motivation, but I wanted to emphasize this this relation, how these things fit into the picture.
Hello. Okay.
Yeah.
So once you have this yeah, K0 and GW0 group, like how much information from the original ring or schemes you retain? Like
How much?
why do you want to consider these groups?
Okay. So I want to, well, I suppose a priori you want to consider these groups over schemes because you want to understand how the collection of vector bundles behave on the scheme, right? Like you want to understand how vector bundles behave. So I think that was Grothendieck's original motivation.
Okay. Okay.
Yeah. So you want to understand vector bundles ultimately.
Yeah.
That's what you want. Yeah. So
Okay.
why you
Yeah.
want to do that? Because I don't know. Why do you want to understand like the derived category of the scheme?
Okay. Yeah.
It
Okay.
has many applications.
All right. Thank you.
Any other questions? Okay. So the reason why I write this is because so it turns out that this is a shadow. So so when you look at this, it looks like it should really carry on to the left, right? And it should be like it should be like a piece of something which is like longer or maybe a lot more abstract, and indeed it is. So this is it. And indeed, so this is a shadow of okay, so the fundamental fiber sequence of spectra. Okay. Well, let me write that down, and then I'll explain. So it's boldface. Okay, then you take homotopy fixed points. Sorry, homotopy orbits. Then GWR. For some reason, people call the Wick group L. Okay, so this is indeed a shadow of something which is like a lot more general. Let me explain. And if you're not comfortable with spectra, you can just think of so a spectrum is just it originally came from reduced cohomology theories. So reduced cohomology theories are equivalent to spectra, but a spectra is just a sequence of spaces that have maps between the suspension of one space to the other. They're very, very, very important in algebraic topology. But if you're not comfortable with that, just think of a sequence of spaces that encode homotopy groups. Yeah. Better. So this is a fiber sequence. Okay. And let me explain these terms. So here. So I won't go into this in detail because then takes us too far afield. Okay. So this boldface K goes from so this is okay. So this is idempotent. I'm gonna throw some words by now. Idempotent, complete, stable, infinity categories. And this is spectra. Okay. So I assume you're not comfortable with this. So think of K, boldface K, as like eating derived categories of a ring or a scheme. Okay. So it takes a derived category and it spits out a spectrum. So that's maybe the best way to think about this at the moment. So this is called as so boldface K is called non-connective. So non-connective. Okay. That's what this is called. And GW. Okay, so then this guy is now called Poincare. These are Poincare infinity categories. So this was the new innovation that was done by the 9 authors. They rewrote the framework to fit this setting. So this is called okay, so there's a big name, Kirby Van Dyck Lit theory. Okay. So if it wasn't a boldface, you would drop Kirby. But, yeah, so I consider boldface. And so again, L also goes from the same guy. Okay. This is known as, well, I call it boldface alpha. I think there's other name as well, like universally decorated alpha. But anyway, it's meant to generalize the Wick groups. So I'm not going to go into the definitions of these because that will just take us too far. But the point is that so the intuition I'm trying to convey is that so these guys will eat the derived category of a scheme or a derived category of a ring, and it will spit out a spectrum. Okay, and then the homotopy groups of the spectrum will give you the higher K groups and GW groups. In particular, it will lead. This will be part of the exact sequence associated to this guy. Okay, and but what I do need to tell you is that the main property that is required that we use of these guys, so they are all examples of something called localizing invariance. So localizing invariance. Okay. Invariance. So these are all localizing invariants. So what does this mean? So I won't give you a formal definition, but I'll give you the intuition. So they send. Maybe I can say the formal definition in words. But, let me write the intuition down. So they send some notion. So that's why I put in quotation marks of short exact sequences exact sequences A, B, C to cofiber. So a cofiber sequence of spectra. So if E is a localizing invariant, and you should think of a cofiber sequence as something that encodes, so this gives a long exact sequence of homotopy groups. Okay, so this is what it does. And by short exact sequence, so a short exact sequence is also a cofiber sequence, but a cofiber sequence of these categories. Okay, and then okay, no. So by this I mean something of the form. So if to be comfortable by this, you can think of this as, say, the inclusion of a subcategory. You can think of it as maybe a triangulated subcategory of B, and then you can take the Verdier quotient, so B of A. Okay, so where this is Verdier quotient, Verdier quotient. Okay, quotient. So it will send sequences of this form to cofiber sequences which will give you long exact sequence of homotopy groups. Okay, so that's important. That I need to emphasize. And the reason why I'm emphasizing this is because, so as a main example, so when we have a semi-orthogonal decomposition, okay, suppose we have a semi-orthogonal decomposition of a triangulated category, so A1, AN. So for boldface K theory, we get a splitting. So K theory of T will be the direct sum copies. So equals 1 K theory of all the pieces in the semi-orthogonal decomposition. Okay, so which gives us Logan. So I'm going to call semi-orthogonal decomposition SOD. Okay, SODs give computations. Okay. In K theory. Okay, so whenever you have a semi-orthogonal decomposition of a derived category as a K theorist, you're happy because it gives you some hope of computing something. So you just need to know what these individual pieces are, and if you're lucky, you can do that. Okay. Any questions so far? So the whole point of the above is whenever I have a semi-orthogonal decomposition, I have this like splitting, and this splitting comes from this property. Okay. So it's this localization property. And that's how I'm going to compute something. Okay. And then in Hermitian K theory, so something similar happens. So Hermitian. Flora, how am I doing for time? Like,
You still have an hour, maybe 55 minutes.
that's good. Okay, that's good. That's good. Okay. That's fine. That's good. Okay. So in Hermitian K theory, something similar happens, but this is why one extra piece of data. Okay, so I'm not going to define this properly because again, it'll take me too far afield, but I can give you like the intuition so that you can take that away with you. So let me do that. Okay, so I'm going to explain this. So this is Okay. So if this thing is a SOD of U, with some notion of duality, I won't define strictly what it is, but you can, it conforms to your usual intuition. But for now, just and with the duality. But for now, I just want to convey the intuition. So with duality, whatever that means. Again, I'm not defining it, but whatever that means. Okay. But if I have some notion of duality, um, such that, so if I have a duality such that I fix this guy, the guy in the middle, B, and I swap A and A dual. So A dual goes to this guy, and then A dual. So encoded in this definition will be that the double dual will be isomorphic to itself, and yeah, blah blah blah. Yep. So then, so here, when I took K theory of semi-orthogonal decomposition, I just got pieces of the SOD, right? In Hermitian K theory, something similar happens, but you need to understand what the duality does on the individual pieces. The duality will be given by the dual of given by the symmetric bilinear form. I will define that later. But yeah, so in Hermitian K theory, there's this extra datum, and provided this duality satisfies this condition, then the Hermitian K theory of this triangulated category will be the same as, so in the above case, it just it had pieces of K theory only of the SOD. But in the Hermitian K theory case, I'll get a Hermitian K theory copy of the guy that is fixed by the duality. So this is B. And then the guy which is swapped by the duality, I get a piece of that, but only in K theory. So the point is that like there's also like an analogous statement for Hermitian K theory, but I get this statement. I get GW plus K, where GW comes from the fixed guy, and then K comes from the guy that gets swapped by the duality. Okay, I know this is a bit abstract and maybe not that tangible, but in my competition for Grassmannian, this is used, and they hopefully will become a lot more tangible. But this is, I'll come back to this, but I call this a generalized additivity theorem. This was proved by my supervisor. Okay. So this is you can think of this as additivity. So let me just call this generalized additivity. Okay. And right, I think. Okay, so now I can actually start. I've set up everything where I can at least describe the algebraic geometry setup now, to give you the computation. So maybe it's a good time to pause to ask for any questions. So I'll start doing geometry now. Are there any questions so far? So this is basically like my attempt to give you some intuition of the purpose of what I'm trying to do.
So I think you'll sort of answer the question as you proceed with the talk, but I mean, how stringent is it? It seems like a hard condition to sort of construct a bilinear form in general, like something globally defined, say on a vector bundle. Like for P1, like are there sort of simple examples? I mean, I guess you'll do one on the Grossmannian or something, but what can you say about construction of bilinear forms?
So the way we compute, like you do things in general, is that you don't need to construct bilinear forms. You just consider the space of them. Does that make sense?
Yeah, I mean, sort of part of, I mean, part of trying to construct the group or compute the group is because you don't know how to otherwise construct even actual representatives or.
So we want to understand the space of such things, right? So to understand the space of such things, I don't actually need to construct each individual example. Does that make sense?
Kind of. I mean, I'm just sort of wondering if there's maybe some natural constructions. I mean, like, you know, when we construct vector bundles, even just say on a variety, right? We start with, say, the tangent bundle and then the cotangent bundle, and then we look at the exterior powers. So if we were going to say, well, let's try to construct a bilinear form, you know, what's sort of the simplest or most natural way to try to sort of do that?
I'm not sure. in my experience, I've never needed to do that. Maybe someone more qualified than me can give you a better answer, but I've not needed to consider these issues. Maybe you could, maybe you can consider sections of the exterior power bundle. I'm not sure, but I've never needed to do that, so I don't think I can give you a proper answer to that question. But at least it's not necessary to what I need to consider.
Okay, thanks.
Okay, sorry. Yeah. Any other questions? So you'll see later that basically when I state the computation for the Hermitian K-theory, actually the datum, which is additional, yes, it is like the space of bilinear forms on the Grassmannian, but actually this is given by the line bundles on the Grassmannian. Okay, this is why I emphasized the curly L for the scheme case. And again, I will say this later, but what makes it really nice is that the line bundle of Grassmannian, least over fields of characteristic 0, is the Picard group is just Z, right? So it's generated by the top exterior power of the tautological bundle. So actually, if I just understand powers of this line bundle, then yeah, so given that this datum, XL, where did I put it? Yeah, so given that I tell you, and I hope you believe me, that the datum is given by the scheme and the line bundle. If I understand powers of the tautological line bundle, the top exterior power of the tautological subbundle on the Grassmannian, then somehow I get like a complete computation of this. So this is what you'll see, and this is what makes it interesting. So I don't need to construct any bilinear forms, at least in my case. But what makes it work is that the Picard group of the Grassmannian is Z. So yeah. So anyway, yeah. So that's what it makes it work. Basically. Any other questions? Okay, cool. So let me do some geometry then. So we'll be interested. So we will be interested. And so I want to consider perfect complexes of, so I denote Grassmannian Kn by this, and F will always be, so F equals field of characteristic 0. Okay. And by perfect complexes, I mean, so a full subcategory of the usual derived category, but then locally, so I can find an open cover such that locally the complex will be quasi-isomorphic to a bounding complex of finite generated of finite vector bundles. Okay, so dperf is all those complexes which locally are quasi-isomorphic to bounded complex of vector bundles, of finite vector bundles. Okay, so this is what dperf is. So the category of, and the reason why we consider this is because this guy is idempotent complete. Anyway, so complexes. Okay, so okay, okay. So then there's a result by no, oops, no. So what makes this computation work and what we use is that this guy admits a full exceptional collection. So full exceptional collection. Okay, so okay, so I have to explain my notation. So let me just write it down. So S lambda U lambda is, okay, I'll explain everything. Okay. So it's a bit of a mouthful. Okay. Anyway, so what is this? So okay, so here Oops. So Q is the tautological bundle of rank K on Grassmannian A and F. Okay, so this sits in, so fitting in short exact sequence. Okay, so for Grassmannian, there's something called the universal exact sequence, universal short exact sequence of the Grassmannian. And here Q, I'll take this to be rank equals K, and this guy will be of rank n minus K. So notice I've taken Q to be on the right. I don't have to do that. I could also take it on the left, but just the way things worked out technically, it was more convenient to use this convention. But I could also take Q to be on the right, and you can call it a subbundle. So, but I for purposes of what I want to do, I just take it on the right. I just take it on the right rather than the left. But this is called the universal exact sequence. And somehow so maybe a good, if you're not familiar with this, maybe Google understand. So this comes about because we understand the functor of points. So we understand the functor of points on Grassmannians very well. So I learned this using Blackhill. Well, he has a section on this, but yeah. But anyway, that's what Q is. Okay, so then let me then explain what lambda is. Okay, so then, okay, that's Q, and lambda in this guy. So K minus K is a Young diagram. Okay, Young diagram. Fitting in a rectangle of size K and minus K. Okay, so let me draw this. So this looks like this. So if I have a rectangle of size K and minus K, a Young diagram will look something like this. So in general, you have like boxes. Lambda, and as a sequence of numbers, one normally writes lambda 1, or lambda k, where lambda 1 is bigger than lambda k. These are positive, well, yeah, usually taken to be positive integers. Okay, so these are Young diagrams. They're very important in, well, at least in this context. But they come up in like partitions and this kind of combinatorics. Okay, and then S lambda q is the Schurfunktor corresponding to lambda. Okay, so what is a Schurfunktor? Before I tell you what Schurfunktor is, let me perhaps give you examples. So examples. So I only learned of Schurfunktors when I was thinking of this problem. So I don't know how many people know what Schurfunktors are. So let me just explain. So if I let lambda be the Young diagram given by, if I just take ones everywhere. So diagrammatically, this corresponds to k and minus k. This corresponds to just a column. Okay. Then the Schurfunktor corresponding to this guy, I'm just going to use the B, and I'm just going to deal with vector spaces, just give you examples. This corresponds to the kth exterior power of B. Okay. So this you can prove. But anyway, this is what it is. And then for the other extreme case, if I let lambda equal to, I suppose, m 0, 0. Okay. So diagrammatically, this corresponds to like a row this time. This is of size. So, then in this case, it's the nth symmetric power of V. Okay. So the intuition of shear functors is meant to be something that you could say extrapolates, or is meant to be like a generalization of exterior powers and symmetric powers. So it's a framework that encompasses both of them. Okay. Okay, and maybe something which is not that. So S21. So the Young diagram corresponding to 21. So this looks like this. This is actually isomorphic to the kernel of the natural map where you just concatenate. So yeah, so it's meant to be like a general framework that encompasses these things. Okay. So in general, so the definition, I won't define it in rigor, like in all its detail, but I'll give you names and you can look it up if you're interested. Oops, that's the wrong. Tensor power. Okay. So where by absolute value of lambda, so bar lambda, I mean the sum of the components, and C lambda is called the Young symmetrizer. Is the Young Young symmetrizer. Okay. And the point is that C lambda, by this I mean I take the image, it's defined to be the image of how C lambda acts on this guy. Okay, and it will act by permuting the components of the tensor product. So if you're interested, you can look this up. But these are like the examples, and this is the intuition. Okay, questions? So this is, I think I've explained. Yeah, so I've explained what this is. It's so you take shear functors of the tautological bundle, and you index over all Young diagrams living in this rectangle. Okay, of size k by m minus k, and this is a full exceptional collection, and this will generalize, for example, the exceptional collection given on projector space. Okay. So, and as a reference, you can look at Krapanov. Cool. Okay, so I'm almost there. So as I mentioned earlier, so one final thing before I can actually state the theorem. So note that. So note. It's the Picard group of the Grassmannian and is isomorphic to Z, and this is generated by top exterior power of the tautological bundle. Okay, so that to make the computation, so that to have a complete computation, we just need to consider so we just need to consider tensor powers of this guy, right? Okay, so this is what we're going to do, and because I'm thinking of this as an element of derived category, I will just write. So this is quite common. Right. what's also important here is like you need to consider shifts of this guy to obtain the entire picture. So shifts, I mean shifts as in shifting of chain complexes. You shift it to the left or the right. When you're dealing with spectra, you consider suspension. But anyway, so you just think of this as shifts of chain chain complexes. So minus r. So chain complex. Okay, so if I write, well, when I write r here, I mean this. This is shorthand. Okay, so now I can state the thing. Okay, so the computation splits into two parts. Okay, so part one and part two. Okay, so f will always be a field of characteristic 0, and I've defined q as above. So in the above notation. Okay, so GWR of Grassmannian, Kn of a field of characteristic 0 with line bundle depth of q, and you'll see why I will take to the tensor power n minus k is isomorphic to the following. Okay, so it will be just copies of k theory of f over some index, which I will explain. So I will use the following symbols, and I will explain what these mean. So this, when the dimension of the Grassmannian is odd, we have this guy, minus 2 of f. So again, I will explain all these symbols. So I'll explain the exponents. One half of a minus k. Where, so in this case, so this is true whenever n minus k is odd and k is congruent to 2 mod 4. And oops. So we get this one in all of the cases. Okay, otherwise. Okay, so we get only copies of k theory when the dimension is odd. We get this guy when n minus k is odd and k is congruent to 2 mod 4. And we get this guy otherwise. So the only difference between this guy is the shift. So here is r, and here you get like an extra shift of 2. Okay, so let me explain what this is and this is and this is. Okay. Okay, so r of k n minus k is equal to the number of Young diagrams in rectangle of size k by n minus k. Wait. So if I have a rectangle of size k n minus k, I'm considering all possible Young diagrams that fit into this rectangle, and one can compute that is actually just n choose k. Well, actually, more general. So KL is n plus L. Sorry, k plus L plus k. Yeah. So you can compute that. It's an interesting combinatorial exercise. That's good. So that explains R. So let me explain what this symbol is. So S of k n minus k is the So I will use the terminology, then I'll explain what the terminology means. Is the number of symmetric Young diagrams in such a rectangle. Again, I'll explain what symmetric means. It's a very natural notion. And AK is the number. So S for symmetric, A for asymmetric, or asymmetric. Okay, so what do I mean with this? So asymmetric diagrams in this rectangle. So what do I mean? I mean, so let me tell you what this means. It's a very natural notion, or definition. So for lambda equals to lambda 1, lambda k, in rectangle of size k by L. So let me draw this rectangle for you. This is k, this is L, this is lambda, okay? So this, we can define the complement lambda to the c, and this is defined to be, so what you do is you take the difference of each row of lambda within the rectangle. So you do lambda minus L minus lambda k and L minus lambda 1. And so pictorially, what this means is if this is lambda, lambda complement will just be what's not in lambda within the rectangle. So if this is lambda, the lambda complement is just this guy, okay? So you take the complement of the Young diagram within the rectangle. Can't use different colors. Anyway, yeah. So this is what it is. So you take lambda within the rectangle, and you consider what's not in the rectangle, and you consider the Young diagram of that. So this is what this is, okay? And we say lambda is symmetric if lambda is equal to its complement. Okay, like for example, you can consider the rectangle 2 by 2, and if you consider lambda here of just the one column, then lambda complement will just be the same thing. Okay, so this is what we call what we say when lambda is equal to its complement. We say it's symmetric, and we say it's asymmetric when lambda is not equal to its complement. Okay, and we can compute these numbers. So SKL, so this is the number of symmetric Young diagrams. This is actually equal to K prime plus L prime over K prime, where K prime is defined to be the integer part of K over 2, and L prime is defined to be the integer part of L over 2. And then the asymmetric Young diagrams is just the number of Young diagrams minus the symmetric ones. So we can compute these numbers explicitly, so that in this computation, we really have an explicit computation. It really is like we can compute this on numbers. Okay, so this is part one of the statement of the theorem. Any questions about this?
Previous question. So can you choose a particular representative and then sort of go back and then sort of make that sort of explicit, or is it still just sort of really
So representative of what, sorry?
Of the right-hand side, right? So you've given sort of an isomorphism, and so can you sort of look at a particular class and sort of find a particular representative that can be, you know, sort of described explicitly, if that makes sense?
Oh, so you're saying if you can find, wait, do I understand your question? So if you're saying, can you basically trace through this isomorphism? Is that your question?
Yeah, basically, yep.
I think in principle, yes, but I think in practice it's very difficult. So basically, the way we prove this is we basically we really try to we use this additivity theorem, and even using, for example, additivity for K theory, I think it's all of these things are ultimately given by inclusions, right? But to actually understand what it is explicitly, one has to really understand the proofs of these theorems, which can be done, of course, but it's a lot of hard work.
No, that's already very interesting. I mean, like for P1, of course, the vector bundle splits, but then aside from that, already it's complicated. So that's interesting. Yeah. So thanks.
Yeah. So, but I suppose, I mean, I write it like this because somehow it just aesthetically it looks very easy to write down. I suppose that's why I do it like this. Yeah. Any other questions? So hopefully by now you at least I can say that I've explained it. I've tried to explain everything that I've written in this theorem. Yes. Any other questions? Okay, so that's part one. Let me tell you part two. So to state part two, to state. So part two. Okay. Okay, so note that we have canonical embeddings of Grassmannians. Okay, so when dealing with the Grassmannians, there are two canonical closed embeddings we consider. There is the following embedding, and there is the okay. So these are the two canonical embeddings. So this embedding J, you can literally think of this as including a subspace into a space of higher dimension. Fine. Here you can think of adding a basis vector to the very end of each subspace you're considering. So this is what I'm doing here. But anyway, so these are the two, I think, usual embeddings you think you associate with the Grassmannians. And this is important in the statement of the next theorem. So the second part of the theorem. Okay, so in the above notation, we have a split vibration. Split vibration of the spectra. Oops. So I emphasize split. Okay, less than n, r and z. Okay, so what is it? Okay, so it looks like this. So GW, so the exponent here will be r minus n minus k. So you get like a shift. Yeah. Plus 1 n, k minus 1, n minus 1. That of q tensor n minus k. Okay. So there's a map which is induced by the push forward. It is not obvious at all why this map makes sense and why I should even consider this, but I'm telling you it makes sense and we should consider this. But this is not obvious at all why this makes sense. But I ask you to believe me. So the next term is that of q tensor n minus k minus 1. And then there's a map induced by the pullback of J. Okay. Plus 1 k minus 1. Okay. Right. So the point is that I can write the middle. So the reason why I emphasize the word split is because I can write the middle guy in terms of a direct sum of the other two guys. Okay. And if you look above in statement of part one, So the exponent of the tensor on det Q in part 1 was n minus k. Okay. And then in the statement of part 2, the exponent of the tensor is n minus k minus 1. So it's 1 below. Okay. But the point is we can write the middle guy in terms of the direct sum of the outer two guys. And if you look here, the outer two guys, n minus k is equal to the difference of this guy, n minus 1 minus k minus 1. So we can compute this using part 1. And also we can compute this guy also using part 1, because the exponent here is n minus k minus 1, which is the difference of these two guys. Okay, so we can use part 1 to compute the outer two sides of this fiber sequence, and then the middle guy will be the direct sum of the outer two guys. Okay, and so it turns out, so this concludes as it turns out, this concludes the computation. Computation as it is known, at least when in the case where 2 is invertible, that GW of XL is isomorphic to GW of XL tensor M2, where so M is also a line bundle, and I'm saying that this guy will be isomorphic to the guy on the right hand side, where I take an even power of a line bundle tensored with L. So i.e. GW is two periodic with respect to L, tensor powers of L. Okay, so there's two periodicity happening. Okay, and so a vague intuition for this is if I consider maps of this form, then I can obtain because it's a line bundle, so I can take its inverse, right? And I can get a map of this form. And because tensoring with a line bundle is an equivalence, quote unquote, maps of this form will give me maps of this form. So I still run through all vector bundles. So this is where the two periodicity comes from intuitively. But anyway, because we have this two periodicity, then the computation is complete because we can compute this guy. Oh, sorry, in part 1, we can compute this guy with respect to some power of the det Q. And then in part 2, we can compute this guy with the power of det Q reduced by 1. So you have both parities. Okay. So that is the conclusion of the statement. Okay. Any questions before I sketch the proof? How long do I have for? How long do I have? Sorry?
17 minutes.
17 minutes.
Oh,
Okay.
16 actually, yeah.
Okay, that's good. Okay, that's fine. Cool. So let me give a sketch. Okay, sketch of part 1. Okay, sketch of part. Okay, that's fine. Okay, so the idea is to use the generalized additivity for GW. So part 1 is literally done. So this is literally computed using this guy. So using this. Yeah. Okay. So what to do? Okay. So we need to understand. We need to understand how sheaf form. So the duality given by L will be given, so is given by sheaf form of blank. And by sheaf form, I mean really derived sheaf form, because I'm working in derived category, don't I? I will not write that. Wait, so det Q tensor n minus K. Okay. So we need to understand how the duality given by this guy affects the exceptional collection. Affects the exceptional collection. Okay. So this is what we need to understand. And this is done by the following. So to do this, we use so in the context of Schur functors, there's a really nice identity called the Hiri identity. Okay, so let me state what this is. So when I have S lambda of Q and I tensor with the nth exterior power of Q, I get something which is the direct sum of Schur functors over some Young diagrams, which I'll explain, where the sum is over all Young diagrams lambda m obtained from lambda by adding m boxes. So you add m boxes to lambda. So graphically, that's what you do with no 2 in the same row. Okay, so I can't add 2 boxes in the same row. So in particular, if I take the top exterior power of Q, so that of Q, I just add 1 box to each row. So you can think about that if you don't believe me. So graphically, it looks like if my Young diagram was something like this, then what I'm doing is I'm taking like a column and I'm just adding them to this. So it gets like, so that's what I'm doing. Okay, and because of this identity, so we can therefore define S lambda Q. So I'll explain the notation. Tensor C. For all lambda 1 equals, sorry, for all lambda equals lambda 1. So basically the point is I can define this when lambda may have negative numbers, where okay, and C is an integer such that lambda I equals mu I plus C, all I. So the point is, like, using this identity, I can define this for Young diagrams which have negative components, which may have negative components. And given that, so one is able to show. So this is where I use the characteristic 0 assumption. In characteristic 0, so this does not work in characteristic 0. That so if I take the dual of this vector bundle, and by dual I mean dual respect to the structure sheaf. I get the following vector bundle. Okay. And this means so this was the duality I needed to consider. So this is, because these are finite vector bundles, I can pull this out. It's K. And then this is, let's say, minus K, minus lambda 1, 2. And then I can use the Peary identity again. So n minus k minus lambda k. Okay, so n minus k minus lambda 1 q. But then we look at this guy. So what is this guy? N minus k minus lambda k and n minus k minus lambda 1. So when I looked back at the complement, this is exactly what it is. We're just taking the complement of the Young diagram within that rectangle. So if you look at this, L minus lambda k, L minus lambda 1. So under this duality, which is why I chose the exponent n minus k, you really do get the dual of s lambda q. So you get the complement of that. So this is s lambda q. So it really does behave nicely under this duality. Okay. Okay. So, but then this means the symmetric Young diagrams are fixed by the duality. Okay. So under this duality, the S lambda Q is mapped to its complement, and so therefore the symmetric Young diagrams are fixed by this duality. Okay, so this explains. So we get. So therefore get. So we get part one by generalized additivity. Generalized additivity. Okay. So because we understand what the duality does, so we're generalizing. Where is it? Yeah, so we use this because we understand what the duality does. We understand the fixed points, and we understand A will be the asymmetric Young diagrams. So we can use this theorem to compute this. And let me remark. So sorry, if you noticed in this theorem, there's a shift of r minus 2 in a very annoying case. Let me explain where that comes from. So the shift r minus 2 comes when, so intuitively, under this duality, the symmetric Young diagrams that are fixed under this duality correspond to give you a symmetric bilinear form. So when symmetric lambda, sorry, it gives you a bilinear form of the following form. So S lambda q. So under this duality, you'll be able to obtain the following bilinear form. I won't explain precisely where this comes from, but intuitively, this is what you get. But the shift r minus 2 comes from the fact that in the case described above, this thing will be it will be actually skew symmetric. Skew symmetric. Symmetric. Okay, and this comes from. So this is intuitively induced by the following pairing. So if V, so V is of rank n, so rank of V is n. So this is that V. Okay. So maybe this may be skew symmetric, right? Maybe. if you have V as of rank n and suppose that n minus k is equal to k, right? You can have these things. So then this would be equal to k. So this pairing may be skew symmetric. Okay, so it depends on how many swaps you need to do, right? And yes, so this is where the skew symmetry comes from, and this is where the shift R of -2 comes from. Okay, right. So that's the sketch of part 1. Any questions? Okay, so sketch of part 2. Actually, wait, did I get that right? Sorry, don't. I just want to make sure I have the correct bilinear form. Yeah, that's right. Yes. Okay, cool. Anyway. Oh, sorry. There was meant to be it. If it's meant to be no, that's fine. That's fine. Yeah, that's fine. Sorry. That's fine. Anyway, sketch of part 2. Okay. How do we do part 2? So part 2, we need to use we use. So we need to use this property here. So we need to send short exact sequences to fiber sequences. So we use the localizing property. Right. So to do this, we need to consider a suitable short exact sequence of, say, triangulated categories. Right. So consider triangulated subcategory T of D perf of corresponding. So generated by, okay, so this guy is equal to S lambda Q as a full exceptional collection where my rectangle was of K n minus K. So K and minus K. So I'm going to consider the subcategory T generated by all Young diagrams lying within this rectangle. So T is equal to the triangulated subcategory generated by all Schur functors living in the rectangle of size K, n minus K minus 1. So this will be n minus K minus 1. Okay. And then one can show, similar to the above, T is closed under the duality Schriefhahn n minus K minus 1. Okay. Because intuitively, because this has exponent n minus K minus 1, and then the length of T is contained within n minus K minus 1. So this is why it's closed intuitively. Okay, and then further, because T is generated by exceptional objects, it is both left admissible and right admissible as triangulated subcategory, so that we have a semi-orthogonal decomposition given by the following. T perp is an SOD. Okay, where T perp is all the guys which kill T on the right. Okay, so in particular, this is SOD. Okay, so there's no morphism from right to left. so that the Verdier quotient of T is equivalent to T perp. Okay. So we need to use that. So then localization gives a fiber sequence of the form GWR T GWR plus F Okay, because T is closed under the duality will induce a duality on the Verdier quotient, which is equivalent to T perp. So we have a duality on T perp. But the point is that this is a fiber sequence, okay? So then we are aiming for the following fiber sequence, and we will get this following fiber sequence by proving the following diagram. So theorem, so part 2 is proved if we can show. So so here comes a very big, not big, but a diamond-shaped diagram. So oh my god, right side. Laura, how long do I have left?
-2 minutes. So
Minus
be
2 minutes.
nice.
Okay.
Yeah, if you can
Yeah,
wrap
so let me
up.
just finish this. Let me finish this diagram then.
Okay, yeah.
Yeah, that's fine. Okay. Yeah, I'm almost done. I just need to finish this diagram. So then I can talk more about it later. Um, okay. So it will be done. So this diagram. So our computation will be complete if you can show that the diagonal arrows in this diagram are equivalences, and this is done. This is done by showing. So J star. So this pullback from T into this one, and okay, so LT compares with the push forward. Into T perp, where here I mean the left mutation, through T. So this is a common concept in helix theory. So this is done by showing that these two maps map exceptional collection to exceptional collection. Okay. And this is what we do. So the pullback is easy because the Schur is given by tensor operations. So pullback commutes with tensor operations. But the last guy is very difficult to prove, and this requires like to do with to use mathematics using like Schur functors, using the Borel-Wheel-Bott theorem, and this is where Chung Kai did a lot of work. So this involves some very interesting geometry. So if you're interested, I can talk about this later, but I've run out of time. But anyway, so this is what is required to prove this part of the theorem. Yeah, and sorry for running out of time. Thank you for your attention.
Are there any questions or comments?
So have you tried to sort of set up like sort of the general case for like Gmod P or something like that? Like, is that
So you mean of a like
like
of a
for
ring
like
with
flag for so for flag varieties sort of, or general,
yes,
like
yes,
just flag
yeah.
manifolds or something like this?
Yeah, so I believe this is possible for flag varieties when, again, you're working the characteristic zero assumption. The reason why I haven't done this is because I simply don't have time. But I believe it's genuinely possible. Because, like, again, flag varieties also have this full exceptional collection. And I believe all of this should also generalize to that case as well. But I've just not had time to think about it. But I think it's very possible. Yes. I think, but the more interesting case, I think, is if you drop the characteristic zero assumption. And that, I think, is more interesting because the reason why we use characteristic zero is Schur functors are equivalent to Weil functors in characteristic zero. But if you drop that assumption, then that is no longer true. So then the interesting question is, how do the dualities behave in this context? And I think it's still possible to do this because, for example, Efimov and other people have generalized Kapranov's results of full exceptional collection in those instances. So Efimov does it over the integers, right? So Grassmanni over the integers. So it should be possible to understand the dualities in this case, but I think one needs to have a deeper understanding of this mathematics, and I don't have the time to do this. Yes. Does that answer your question?
Like Gmod P or something, and you see sort of how the other root systems interact. If there's sort of another sort of a more representation intrinsic formulation
Sorry.
of the problem as well.
Yeah, sorry.
There's
sorry,
two
sorry,
directions.
sorry.
Yeah, there's sort of two directions you could try. Yep.
Yeah, sorry. I know nothing about root systems or this kind of stuff. I know nothing, so I'm totally ignorant in this field. Yeah, it's someone else who knows more about this can do it, but I don't know nothing about parabolic subgroups or Pearl subgroups. Yeah, sorry, I'm very ignorant. Any other questions?
Any other questions? Maybe I'll ask a stupid question about the generalized additivity theorem. So,
Yeah, it's
so
not stupid.
I actually know very little about derived categories, but I suppose the so for any Grassmannian, is the SOD only consist of like three things like A, B, and A dual, because it's how you.
Oh no, so I mean, the reason why I write A, B, and A dual is because here B is fixed by this duality, right? So
Okay.
the first step was to understand how I can use this theorem in the Grassmannian case, and so wait, let me go back. There is the. Where did I write it? Ah, here. Okay. So this is quite a classical result by Kapranov, right? And morally, like, so similar to how one used this like exceptional collection of projective space, like in terms of the shifts of the line bundles. And my supervisor did a computation using that exceptional collection. So morally, it should have been possible to use this exceptional collection to compute the Hermitian K theory. But then to do that, one first had to understand how the dualities behave on this. And this is why I took my duality to be where is it? Sorry. Okay. Yeah, this is why I took my duality to be det of q to the tensor n minus k, because it's exactly with that duality that that a Schur functor is mapped to its complement. So like using that duality, then I can organize into A, B, A dual, where B is the ones which are fixed and A are the ones which are asymmetric, so they map into each other. So like note, for example, like if you take lambda complement, you get back lambda, and lambda complement equals lambda if and only if a k Oh wait, so maybe but for there to be symmetric Young diagrams, you really need your dimension of the Grassmannian to be even, because if it's odd, so k and minus k equals lambda plus lambda complement plus 2 lots of lambda. So if you have lambda equals lambda complement, then you would have like the area of the rectangle is twice, so 2 times the size of lambda. So this is only possible when this is even, which is why you only get you only in the odd case you only get copies of K theory. So to answer your question, you only use I use this theorem, and the reason why how I was able to use this theorem because I chose the duality in the correct way to apply this theorem. So you need you need the fixed points, and they are definitely in the middle. Yeah.
I see. Yeah. Thank you very much.
Yeah.
Okay.
So, yeah, I'm not stated the theorem like precisely. Like if I had to do that, it just would take me too off the field. But this,
Right.
the idea is this.
Yeah. Okay. Are there any more questions? If not, then let's thank Sunny again.
Thank you.
Yeah. Thank you very much for the nice talk.
Thank you. Thank you. Cool. All
Yeah.
right. Hopefully see you soon.
Yeah. See you later.